Welcome back to ChemDoctor, and this is the fourth video in the series on thermochemical equations. And what we're going to do in this one is start basically describing Hess's law, although everything that we've done up to this point, the last three videos, are based on Hess's law. The first thing, the first point being that the amount of energy that's either released or absorbed for a chemical reaction is based on the balanced chemical equation. All right, so for this reaction, which has been the model reaction that I've used for these videos, the reaction between propane and oxygen to produce carbon dioxide and water. It's a classic combustion reaction between an alkane and oxygen. The products are always CO2 and water. It's an exothermic reaction. It's a thermochemical equation because we're provided with the information in terms of the enthalpy, the change in thermal energy that is released by this reaction. We know that it's released, that it's exothermic, because there's a negative sign that denotes or defines this number that follows. All right, and then I'm using underneath the fraction bar, I'm using some terminology here that may or may not be familiar to the student, depending on who your professor is or your teacher. What this number means per mole of reaction. This just emphasizes the fact that this amount of energy that is released is based on this balanced equation. So when we have exactly 1 mole of propane that burns in the presence of 5 moles of oxygen, and the reaction is allowed to go to completion, 100% completion, where we produce 3 moles of CO2 and 4 moles of oxygen, then this reaction is also going to produce 2,221 kilojoules of energy, and we can consider this amount of thermal energy released as operating like the products of this reaction based on the stoichiometry of the reaction. Now, in Hess's law, when we reverse a reaction, the rule is that the delta H will be the same in magnitude for the reverse reaction, but opposite in sign. All right, so in other words, if I decide we're going to run the reverse reaction, all right, so let me label it this way: reverse reaction, all right, and it's going to be 3 CO2s plus 4 H2Os. So we're going to combine the CO2 and the water, and we're going to produce propane and oxygen in the reverse reaction, and I gapped this for a reason. All right, and you'll see what I'm going to do here in a second. I introduced this concept in the last video. Let's just take a look again at the energy diagram for the original reaction. All right, so if we were going to follow the reaction diagram for the top reaction here, it would look like this. The reactants are at higher potential energy than the products. The value for the reactants is H1. If we run this line out, H2 is here. So the products are at a lower energy. If we figure out our gap, so the delta H here is going to be H2 minus H1. This is equal to minus 2,221 kilojoules of energy released per mole of reaction, per the coefficients of the balanced equation. All right, now for the reaction, the way we've written it here, the energy diagram is going to be the reverse of the top one. So let's go ahead and do it. So for this reaction, our the reactants, in the direction I've written this, pick an arbitrary place to start this. So here's our reactants. All right, and then we're going to have our initiation energy, which creates this hump. However, in the reverse reaction, the platform for the products, you see, is higher than the platform of the reactants. So this would be H1 here. And then if we draw a line going across to the products, this is not as, let me just try and get this. All right. My artwork is not the best in the world. Let me try to clean that up a little bit. Okay, now this is H2. If I carry this line out and we do this gap, you see the delta H for this is equal to H2 minus H1. And now, because H2 is greater than H1, this is going to be a positive value, and it's 2,221 kilojoules. So it's the same in magnitude as this number up here, but we're going in the reverse reaction. And if you look closely at this, again, if I draw your attention to the top diagram, you see what we're doing is we're going backwards. So we've started here, and we're going back to this point here in reverse. So the energy gap, the gap between this point and this one is not any different. It's just that instead of going in the forward reaction where this amount of energy is released, we're going in the reverse reaction where this amount of energy now has to be put back into the system, because these products, the propane and the oxygen, are at a higher potential energy in terms of their bonding than the reactants. All right. So now, because we're going into reverse, this system has to absorb energy. So we can treat the energy budget here as if it is a reactant. So I'm going to go ahead and write it in here. And the coefficient in front of this number is a 1, right? It's a 1. So in other words, in order to carry out this reaction, you will have to, and if we're doing it based on the balanced equation, you will have to combine 3 moles of CO2 with 4 moles of H2O and 2,221 kilojoules of energy in order to get it, in order to get the reaction to go to completion to produce 1 mole of propane and 5 moles of oxygen. So we've got to climb back up. We have to climb up this hill. We have to go from the R to the P. We've got to go up in energy. All right. The products are at a higher potential energy than the reactants. All right. Now, what's the problem that we're going to work on? So we're going to say that we got 18 grams of H2O. And what I want to know is how much energy is going to be absorbed. All right. How much energy is going to be absorbed. And by the way, what we just described over here, and I almost forgot myself, is that we're dealing with now the reverse reaction is endothermic. This is an endothermic reaction. Endothermic. All right, endothermic reaction going in reverse. So the system has to absorb energy. All right, so let's figure this out. First things first, we've got like a theoretical yield calculation. We're going to need to get the moles of the H2O. So we're going to take and multiply 1 mole, or 18 grams of H2O times 1 mole over 18 grams of water for a mole. I see that the grams cancels out, and we get 1 mole of H2O that's reacting. Notice that the energy budget is based on the balanced equation, which has 4 moles of H2O in it. So now what we got to do is figure out how much, what the energy budget is for the H2O per mole. So this is going to be, so for H2O, all right, let's take a look at that. What is the energy budget? All right, so it's going to be 2,221 kilojoules of energy needing to be absorbed per 4 moles of H2O. So to find the per mole value, what we're going to do is we're going to take 2,221 kilojoules of energy per 4 mole of H2O. And what we get is that for the per mole value is that it's going to take 555.3 kilojoules of energy per mole of H2O reacted. All right. So now we're ready to finish our calculation, since we already know that what we're doing is we're going to utilize 1 mole of H2O. So I'm going to multiply this energy value per mole times 1 mole of H2O. So moles of H2O cancels out, and we see that this energy, or this reaction, when we utilize 18 grams of H2O, we're also going to have to utilize 551.3 kilojoules of energy. So the reaction, in order to complete this reaction, when we utilize the 18 grams of H2O, the system's also going to have to absorb 555.3 kilojoules of energy in order to produce the corresponding amount of propane and oxygen. All right, with that, I'm going to go ahead and close the video.